So, hello everyone. This is going to be a report on a work first started by Alan Gabriel and on the unusual direction we carried it into. As you all know, during solar flares, the non-thermal tails are usually observed. Now with RESI, here is an example of such an observation. You have the non-thermal tail at the range of several keV and the rest of the distribution, which is usually interpreted as Maxwellian. Alan Gabriel did a work on this back in the 70s, and what he did with Ken Phillips was to calculate the effect on the dielectronic satellites if you add a tail to this Maxwellian distribution. So what happens if you add a tail is that the allowed iron 25 line gets excited more, and as a result the ratio of the dielectronic satellites with respect to this helium-like line decreases. And I'm sorry to say this is a point that has largely been forgotten in the literature, and to make matters worse, the exact opposite is observed. This is a spectrum from the Polish RESIC spectrometer, where you can basically get a temperature diagnostic from the allowed line of silicon 14 and silicon 13. They are temperature sensitive simply because of the ionization equilibrium, but then you cannot match the dielectronic satellites, and you cannot get a good match to observations even when you consider a multi-thermal plasma. So what you have to do is to consider a non-thermal plasma, then you can get a good match to all these three lines. And the non-thermal plasma usually considered is in the form of N distributions, which have this sort of term multiplied to the usual Maxwellian, and the result is a distribution that is a more narrow or more monoenergetic than the Maxwellian. The evolution of the distribution during the flare is such that in the impulsive phase you start at a very high values of N, meaning high departures from the Maxwellian, and then slowly as the flare progresses, the plasma thermalizes. And during the same time you see higher departures from the Maxwellian, you get also strong radio bursts, meaning that this departure from Maxwellian somehow has to be connected to particle acceleration. You can also see these departures from Maxwellian also in the RESI spectrum. Here is the usual fit of one of the flares with a thick target and a Maxwellian plasma, and here is the N distribution added. If you pay attention to the chi-square gets much better if you add the N distribution that is responsible for the dielectronic satellites. The problem here is that the N distribution should produce continuum emission at around only several keVs, which is at the very limit of what RESI can see, but the density, the amount of emission measure that should be associated with this N distribution is in fact higher than the thermal component that seemingly dominates in this image. So what we try to do as a follow-up on Alan Gabriel's work is to construct a distribution which has either a Maxwellian or non-Maxwellian bulk, and then add a high energy tail and look what happens on the silicon spectra. What happens is that if you have the Maxwellian bulk, the dielectronic satellites are affected only very weakly. Here the difference is about 10%, but the tail can change the ratio of these two allowed lines quite a lot. And you only can produce the increase in the dielectronic satellites if you assume the non-Maxwellian bulk. The problem with N distribution is that it is only a mathematical distribution. It has no real physical background. So we try to search for some distribution that actually has some physical interpretation. And it turns out if you consider something called a moving Maxwellian, which is a Maxwellian simply with a velocity drift in one direction, and you write it in the energy terms, you get a distribution that has the same gradient at the range of several keV, where the dielectronic satellites are formed as the end distribution. Now, this moving Maxwellian is also problematic because it is unstable with respect to Bunnemann instability. So you have to search for a distribution that is stable on the timescales of several minutes. And it turns out if you produce something called double layers in flare loops, the double layer is essentially a structure where you have an electric field parallel to magnetic field, and this can lead to additional acceleration of electrons. Now, you should expect this sort of structure in flaring plasma simply because you need electric field to produce the magnetic reconnection in 3D. What Marian Karlitsky did was to simulate the double layers using a particle in cell code, where he put essentially a background plasma and allowed the electrons to be accelerated in the double layers. And he get this sort of stable peak, which in this energy range has the same slope as the end distribution. So what we did next was to consider double layer distribution, which essentially accelerates electrons only in one direction. So it's a moving half Maxwellian. And we consider this distribution, the end distribution, the moving Maxwellian, and the Maxwellian, and calculated synthetic spectra for this. And we also calculate synthetic spectra for a combination of a background Maxwellian and the double layer distribution. Here is the synthetic spectra. For purely double layer distribution, you can get very high dielectronic satellites, as high as you like. The problem is that because the distribution is very monoenergetic, the ionization equilibrium will also have peaks that are formed only at a very small temperature range, so you do not get the silicon 14 line. The end distribution, we already know that this can match the observations. The problem with the moving Maxwellian is that you can get the silicon 14 and silicon 13, but the increase in dielectronic satellites is very small. However, if you combine the Maxwellian distribution with the double layer distribution, you can get both very high silicon 14 line and sufficient increase of the silicon 12 dielectronic satellite with respect to this dashed line, which is a Maxwellian. So the conclusion here would be that the flare spectrum is probably produced in a combination of plasma that contains double layers, possibly very close to the reconnection region, and some thermalized plasma in evolving flare loops. One point that I would like to mention is that if we do have these more monoenergetic distributions, that what should happen is that the ionization edges in soft X-rays should disappear. So this is a theoretical prediction. I would be very happy to see a spectrum where you actually could resolve these ionization edges. So my conclusions: the helium-like lines and the dielectronic satellites offer important plasma diagnostics since they allow you to sample the distribution at discrete energies and give you an option to diagnose the non-Maxwellian bulk of the distributions. And several notes: there are practically no X-ray spectrometers which can produce the required observations now, so we probably need a new instrument, or we need to revisit previous observations. Here the PCS spectra would be a good candidate. And with that, I thank you for your attention.